In Newtonian gravity, planets orbit their stars in ellipses. But if instead of gravity, planets are somehow attracted to their stars by elastic forces on a spring governed by Hooke's law, then the orbit is still an ellipse. The fact that entirely different physics give elliptical orbits is not a coincidence, and the connection between them was found somewhat accidentally by Newton himself in Principia. Newton just wanted to deduce from astronomical observations that gravity obeys inverse square law, but somewhere in the chain of logic, he needed the fact that elliptical orbits can also be given by Hooke's law. Before I give you the gist of the argument, I want to highlight how this isn't something you are used to. The modern way of learning Newtonian gravity starts with inverse square law, and then derive the orbits to be an ellipse, parabola, or hyperbola. Newton didn't know the inverse square law and was trying to deduce that. Instead, he knew that 1. Orbits are observed to be elliptical, 2. The star is at one focus of the ellipse. Newton assumed further that 3. There is a force pointing towards the star, and 4. This force drives acceleration with the famous F equals ma. These 4 allowed him to deduce that gravity has to obey inverse square law. I want to make this logic clear because even Newton got it wrong. He proved the implication this way and thought that he had also proved the other way, but he didn't. This implication isn't how we normally learn gravity, but historically that was the way to go. With all that said, let's see how Newton used the connection to Hooke's law to deduce inverse square law for gravity. Let's say we only know the trajectory of a particle under some attractive forces, but not the velocities or where the center of attraction is. Without any more information, the center can be anywhere because we can fine-tune the centripetal forces so that the particle stays on that trajectory. But for any two candidates for the center S and S', you can imagine that the magnitudes of these forces have to satisfy a certain relation to give the same orbit, and Newton worked out this ratio. Now we specialize to an elliptical orbit. If we take the center of the ellipse to be the center of attraction, Newton worked out that the centripetal force has to be proportional to distance, that is, Hooke's law. But we know the center of attraction should be the star, which is at the focus of the ellipse, so we can use the formula for the force ratios derived earlier. One center gives Hooke's law, and the formula will tell you the other center gives the inverse square law. This is how the two forces connect. We will dig into the details now, but note that this isn't gonna be a faithful retelling of the original argument in Principia unless you want to watch a 12-hour video. Instead, I will add a fair bit of modern hindsight to make it accessible while still being in the spirit of the original argument. Before we really dive into the nitty-gritty, we need 3 preliminary results. The first one is just angular momentum conservation, but here is the geometric demonstration. Let's start with a center and the particle's initial position here. After time delta t, the particle moves to a new position, which forms a triangle with the initial position and the center. In modern terms, this area is half angular momentum times delta t, where we assume from now on the mass is 1. Newton showed this area doesn't change as long as the duration is delta t. If there is no force, then after delta t time, the new area will still be the same with the same base and same height. But even if there is force acting on the particle, as long as the acceleration is parallel to the displacement at time t plus delta t, we still get the same area. Again, same base, same height. So as long as the force always points towards the center, the area in a small time delta t is always half angular momentum delta t. This is a demonstration of how h, or angular momentum, is conserved. I want to emphasize that this only requires the force to point towards or away from the center, but says nothing about the magnitude, even though in the most familiar cases, the magnitude only depends on the distance. This much more lax requirement is what we will be dealing with. The next two results will be gone through a little bit more quickly. The second one is that for an ellipse, if you join the two foci to any point on the ellipse, the two angles made with the tangent are identical. There is a classic number file video to illustrate this with an elliptical pool table. For our purposes, this means that if we draw a line from a focus parallel to the tangent, then these two segments will have the same length, since these angles in the triangle will be the same and the triangle will be isosceles. Also, the defining property of the ellipse is that the sum of the lengths to the two foci is always constant. That's all the properties of the ellipse you need to know for the video, and we go on to the third and final result. This is Taylor expansion to the second order. The velocity is the first derivative of the position, and the acceleration is the second derivative. Of course, there are higher order terms, but we will ignore those. I know this is not comforting for the non-physicists, but this is justified if we are considering the limit of the ratio between two quantities that are of second order. Of course, Newton didn't use this, but this modern hindsight saves us a lot of time to explain what he did in Principia. But yes, here are the three results we will need for the rest of the video. The first step of the argument is this. We can take anywhere to be the center, and we want to figure out the acceleration at this random point P on the trajectory. To do that, we assume that after some time delta t, the particle reaches the point R. I know delta t doesn't look small here, but otherwise you can't even see it, so there's that. We can break down the displacement into two parts, one along the tangent, corresponding to the velocity v times delta t, the other corresponding to the second order deviation due to acceleration. This comes from the Taylor expansion we talked about earlier. But we know the acceleration should point towards the center, so these two lines should be parallel to each other. This parallelism is how we can construct the point Q on the tangent line. Now that there is a geometric construction of Q, we can go back to how this part is due to acceleration. The magnitude of the acceleration A can be found by twice QR divided by delta t squared. But delta t is not a geometric quantity itself. Don't worry, from the first fact we have discussed earlier, we know that the area of this triangle bounded by Q, P, and the center is half angular momentum times delta t. So we can replace our delta t by twice the area of this triangle divided by h. A bit of rearranging gives the acceleration to be qr times h squared divided by twice the area squared. Now h is still not a geometric quantity itself, but we know that it is a constant. So once you set this constant, you can determine the acceleration purely from the geometry of the orbit, which is pretty neat. But one thing to note is that this formula depends on where you put r in the first place, which affects the position of q and everything. Instead, this formula should be understood as the limit of this ratio as delta t tends to 0, or equivalently, as r goes all the way to coincide with p. That's why we can ignore terms of higher order in delta t. If we have a different center, then we can run the same argument and compute the new acceleration to be q prime r times h prime squared divided by twice the new area squared. We can then compute the ratio of acceleration towards different centers. The first part is just some constants related to angular momenta. The second part is the ratio of these little segments, and here's the trick. We additionally draw a line parallel to that joining P and the new center. Now it is easier to see that because of those parallel lines, the two triangles are similar. So if we call this new point A and the original center S, then the similar triangles mean that the ratio Q'(R) to QR is AS to PS. The advantage of doing this is that the new ratio AS to PS does not depend on where R is. So even as we take the limit that R coincides with P, it will always be this ratio. Can we do the same thing to the area ratios? Again, these areas depend on where R is, and we want to remove this dependence. The trick is the same actually, add this line to the same point A, but we have a further trick up our sleeves. We can multiply the numerator and denominator by the same thing. Let's focus on the denominator first. The new triangle has PQ' as a base, so if we multiply by the ratio AP to PQ', then we change the base to AP, so that this becomes the area of triangle APS', where we denote the new center as S'. Okay, so that's the denominator done. What about the numerator? We can almost do the same thing if we divide by PQ instead, because the base of this original triangle is PQ. For the moment, pretend that we didn't see the prime and still shift the base to AP. The numerator will then be the area of this triangle APS, but of course, we can't really pretend that, and so we compensate for it by multiplying the ratio PQ to PQ'. The denominator is just the area of APS' as discussed before. Luckily, this ratio actually tends to 1 as we take the limit of delta t to 0. You can make the argument more rigorous, but essentially, PQ and PQ' are of order delta t, but their difference, QQ', is of higher order, delta t squared, which makes the ratio 10 to 1. So we can ignore this ratio, and the answer is yet another area ratio. The advantage is that we have now completely removed the dependence on R, and there are no limits involved now. Finally, because of the two parallel lines, these two triangles have the same height but different bases, with the height being the distance between the two parallel lines. So the area ratio is also the ratio of the bases AS to PS'. Finally, we substitute this result back into the formula we derived earlier for the acceleration ratio and obtain this result, which involves no infinitesimals or limits and is applicable to all points P on the orbit. This result was in Proposition 7, Corollary 3 of Principia, and if you have made it here, give yourself a pat on the back, since that's 40 pages of Principia with, admittedly, a lot of modern hindsight. Now we put this result aside for a moment and focus on a specific kind of orbit, the elliptical one. We now assume the center of the ellipse is the center of attraction, and we want to figure out the acceleration at each point of the orbit. Of course, you can use the formula we derived before with the limits of some ratios, which is exactly what Newton did, but that requires quite a bit of knowledge about the geometric properties of conic sections. Instead, we use a bit of modern machinery to do this. we set up a coordinate system that aligns with the semi-major and semi-minor axes of the ellipse. If the semi-horizontal axis has length a, and the semi-vertical axis has length b, then we can parameterize every point on the ellipse as a cos theta, b sin theta for some theta. As the particle goes around the orbit, theta changes with time, so we should have the parameter theta to depend on time. Since we chose the origin as the center of attraction, the acceleration should point towards the origin, so it is in the direction of a cos theta, b sin theta. Now we just need to compute the acceleration given that the position is this a cos theta, b sin theta. We take the first derivative to obtain the velocity as such, keeping in mind the chain rule for theta. Now take the derivative once again, which is a bit messy now. Now we want the acceleration to point towards the origin. If the acceleration just has this part, all's good, since it is pointing in the a cos theta, b sin theta direction. If and only if the other part also points in the same direction, then we are done. So at the very least, the ratios of the x and y coordinates have to be equal. Since a and b are not zero, as they are the semi-major and semi-minor axes, we can cancel them in the numerator and denominator. Then we cross-multiply, noticing specifically the negative sign here. Next, we put everything on the right-hand side and notice that cosine squared plus sine squared is always 1, and so theta double dot has to equal 0. This means two things. First, this remaining part that we want to also point in the same direction as the position doesn't really exist, and we are left with this part that definitely points towards the origin. Second, since theta double dot vanishes, theta dot is constant. Therefore, in terms of magnitude, the acceleration is a constant k times the distance towards the origin, which is Hooke's law in 2D. So in the original elliptical orbit, the acceleration is a constant times ps. Finally, we can use the acceleration ratio we previously derived. We now know that the acceleration towards the center of the ellipse is proportional to distance. So by multiplying these two together, we get this formula for the acceleration towards any other new center of attraction. Now we apply this formula to one of the foci of the ellipse as the new center of attraction S prime. Just as a reminder, to construct A, we first construct the tangent at P, and then draw a line from S parallel to PS prime all the way to the tangent. That point of intersection is A. This formula is almost the inverse square law because these h, h prime, and k are constants. So we want to show that this AS is also a constant. To do that, first draw a line from S parallel to the tangent line, which intersects the other green line at a point denoted as B. Because of this parallelogram, we have AS equals PB, allowing us to abandon the point A since PB is the same length that we are after anyway. Next, we enlist the help of the other focus of the ellipse. Let's call this point F for focus. We draw a line from F parallel to the tangent line to intersect the green line, and let's call this intersection C. Now we can split this length PB into PC plus BC. Since we know that S is in the middle of the two foci, this means that B is also in the middle of S' and C, so that we can write this length BC as half the length of S'C. With that, we are done with this old center S and the point B. Finally, we add this line from P to the other focus and use a property of the ellipse that we talked about in the beginning. These two angles made with the tangent line are the same, and CF is parallel to the tangent line, so the two angles in this triangle are the same, which means that PC and PF are the same length. So we can replace this length PC as half of PF plus half of PC. The reason we want to do the split is that now we can see that PC and S'C combine to form PS'. So overall, this length AS is half the sum of the lengths to the foci, which we know to be a constant. After all, this is one of the defining properties of an ellipse. So going back to the acceleration towards this new center S', which is a focus of the ellipse, not only are these angular momenta constants, AS is now also shown to be a constant. So this acceleration towards the focus is really inversely proportional to distance squared. To derive this result, we use the fact that this elliptical orbit can be given by Hooke's law when the center of attraction is at the center of the ellipse, and crucially, this formula for the acceleration ratio of the two centers, which connects Hooke's law to inverse square law of gravity. You might be wondering, what about parabolic or hyperbolic orbits? Those are possible under inverse square law of gravity. Are they related to Hooke's law as well? Roughly speaking, hyperbolic orbits can still be interpreted as an orbit under repulsive Hooke's law, where the force points away from the center, but the magnitude is still proportional to the distance. And again, we can use the acceleration ratio formula to derive that this hyperbolic orbit can be generated by an inverse square law force towards one focus. Parabolic orbits are a bit tricky because Hooke's law, repulsive or not, couldn't produce this orbit, but we can still cleverly use this acceleration ratio formula to derive that parabolic orbits can be produced by inverse square law. For more details, as well as an interesting problem of finding the centripetal force that gives rise to a circular orbit, where the center of attraction is on the circumference, I have made a second channel video for that. Before I give a preview of the next video, I want to give a shout out to a non-profit organization, Give Internet. Across the world, 2/3 of school-age children do not have internet access at home, and that amounts to more than 1 billion children, so they can't access this video or any online resources you might have used. And I don't think I need to elaborate on why the internet is important for education and a necessity for equal opportunities. Give Internet partners with the University of Geneva, MIT Emerging Talent, and others to offer educational programs to students from refugee settlements and underserved local communities. They purchase and distribute laptops to these students who can potentially be developers, designers, teachers, or healthcare workers, but they don't have the internet resources to achieve those goals. You can join this amazing effort by donating to them via the link giveinternet.org/mathmaniac or scan the QR code on screen. Any donation coming from this link will be matched, so your impact is doubled at no extra cost to you if you use this link. Alright, let's get to what the next video will be about. This video established one kind of connection between Hooke's law and Newtonian gravity. If you treat these orbits as being on the complex plane, then there is a simple function that transforms between the two even before you know what their orbits look like. Thanks for the patrons. Like, share, and comment on this video and stay tuned for the next one. Bye!